Now here's a graph of what types of storage are currently in use around the world. This is electricity storage. It's not generation. No electricity is produced by this. It's just storage. So storing up the electricity when there's too much of it and releasing it when there's not enough. And you can see that the vast majority around the world is what's called pumped hydro storage. And we'll talk about that in a second. The remaining little bit, if you expand that, is mostly lithium-ion batteries. But there's also other types of batteries, sodium batteries, flow batteries, and a few others. Compressed air storage, CAES, is the next biggest thing after lithium-ion batteries. Then there's flywheels and hydrogen storage, and we'll talk about most of these in the next few minutes. So at the moment, by far the biggest source of energy storage is pumped storage. This has been used long before concern about global warming. It's a way to balance out energy resources of all sorts. The basic idea is similar to hydropower, but not quite the same, and the difference is important to understand. Just like normal hydropower, you get a water at the high level and water at the low level, and you're storing the energy in the potential energy difference between the high level water and the low level water. The difference is that this works two ways. For normal hydropower, what happens is rain falls up here and supplies the reservoir at the top, and then the water flows down. But for pumped hydro, you are normally supplying the water at the top, not the rain. Though of course if it rains at the top you won't complain. But what you will do is when there's plenty of energy, it's cheap, like say the middle of the sunny day when the solar cells are putting out tons of energy, you will use pumps to pump the water from the low reservoir up to the top reservoir. Then, when you need the power, which might be later that evening when it's dark or a cold period further on, you let the water flow back down through a turbine and generate the electricity back. Now there are these plants all over the world. At the moment, Australia is building a huge new system called Snowy 2.0, a very controversial system, taking the existing dams and reservoirs in the Snowy Mountain scheme and connecting them as part of a pumped hydro program. So it does the same sort of stuff. You've got the Taubingo Reservoir at elevation 540 metres and the Tantanga Reservoir at elevation 1,220 metres, and you have a very long tunnel and a deep underground power station. Underground because it's in the middle of a national park and you couldn't build it on the surface. And so when there's plenty of renewable energy, you pump the water up and then you let it flow down when you need it. Now this is controversial. It's badly behind schedule and way over budget. But you don't need to do it this way. Basically, whenever you've got two valleys at different heights close together, you can build a pumped hydro scheme. It's much easier than normal hydro because you don't need rain in a big river. All you need is two places where you can build dams, one high and one low. And people have done analyses, and there are tens of thousands of sites around Australia where you could do this, even excluding any national park locations. What's the physics of this? Well, it's just potential energy. Energy is mgh, where m is the mass of water stored and h is the height difference between the higher and lower dam. Mass is just the density of water times the volume. Water is about 1,000 kilograms per cubic metre. And the round-trip efficiency is about 80%. So if you put a gigawatt of energy in, you'll get 0.8 of a gigawatt out, which is actually not bad. It's not as good as batteries, but it's actually not bad. And to make it work well, you want to move a lot of water through a great height difference. Now in terms of time, this is not good for very short-term things. If you need power at a second's notice, batteries are your way to go. Because it actually takes probably seconds to minutes to get the water all flowing. You can't just open a valve and get the water flowing through within seconds. It's got a long way to go, and the momentum of all that water moving through means you can't turn it on and off that quickly. So this is often be paired with a battery to give you the quick response, and this to store a huge amount of energy very cheaply and give you a slow response. Now it doesn't have to be water you use to store potential energy, though it usually is. People have been experimenting with actually just lifting concrete weights up and down. This is an experiment in Switzerland where they have a giant crane and they winch concrete blocks up and down to store energy. So when all the concrete blocks are up the top, that will store potential energy, and then when you need to produce it, you can let them go down with the cable running through some sort of generator to release the energy. And there is a company in Australia planning to do this with mine shafts. Basically, there are a lot of disused mines around Australia, and they generally have a large vertical hole in the ground, often going down nearly a kilometre, which was where they originally shipped the miners in and the minerals out. And these are often very nice holes, well lined with concrete and vertical and well designed. And so what you could do is have big concrete weights on a cable, and when there's plenty of power you can use electric motor to wind them up, and then when you need the power you can let them fall down again, and so you can store energy at that. Of course there's a lot less weight in a concrete mass than a whole reservoir full of water, but it's actually much faster to respond, so it has some benefits. Other forms of storage that are used, one that surprised me somewhat is basically spinning gyroscopes, flywheels. You can build these things in a vacuum enclosure on magnetic bearings, so you get a spinning wheel and you spin it really fast when you've got plenty of power, and then you connect it to a generator to spin it down. They don't store huge amounts of power, but they're quite quick at bringing the power in and out, so it's something you can certainly use. And then there's compressed air. Typically this is stored in underground caverns. Might be old salt domes that were used to extract salt or to store oil, but you can pump the air down, pump it harder and harder when there's plenty of electricity, and then let it out to generate electricity later. Or you can have underwater pistons. You could have a giant piston 100 meters underwater, so that you pump air into it, expanding the piston and pushing the water out when there's plenty of electricity, and let the water pressure outside push it back down again and squeeze the air out when you need the energy back. Now the trouble with this is the round trip efficiency is not so good, because generally speaking when you compress air to push it into something, the air heats up, and that heat, unless you do something very careful with it, is wasted. But there are ways to deal with that. You could heat it up but then have some sort of heat exchanger to extract the heat before it goes into your underground cavern or water tank or whatever it might be. But that still adds to the complexity.